Welcome everyone. In this lesson, we're going to introduce the idea of limits, and this is going to really kind of set the stage for kind of our actual definition for what the derivative actually is. So we're kind of working our way up to be a little bit more precise when we talk about, well, what is a derivative? And so we're going to need this gadget which we call a limit. So we're going to start with our limit definition. What is the limit of a function? So let's read through the definition, and then we'll kind of talk a little bit about what this definition actually says. So we say that the number L is the limit of a function g of x as x approaches a, provided what happens? G of x can be made arbitrarily close to this number L for all x values that are sufficiently close but not equal to a. And the notation that we're going to use is right here. So the way we kind of read this, it's the limit of function g of x as x approaches a, and this limit is equal to L. All right, so what is going on here? All right, so looking at this notation, let's kind of unravel this notation a little bit. And what's going to happen is we're going to let our input values, our x values, get closer and closer to the number a. So as our input x values get closer and closer to number a, we're going to see, so we're letting our, let me open that or not cover that up. What we're going to see is we're interested, what happens if we take input values that get closer and closer to this x value of a, this some number a. And what we're going to do is we're going to measure what happens to the output of our function. So we're going to take all of these inputs and we're going to plug them into our function, and that's going to give us the output. And we're going to see what happens to our output. And what happens is our output gets closer and closer to the number L. And this is what a limit is measuring. It's measuring what happens if I take an input and I let my inputs kind of change and I let them get closer and closer to this number a. So I'm measuring what happens as my inputs get really close to that number a. And what happens is the outputs then, the output is g of x, those values get closer and closer to the number L. And that's really what this limit is going to do. And so essentially, a limit describes what happens near x equals a. So this really describes what happens to our function near x equals a. So that's going to be important, this idea of being near. All right, so let's kind of see some examples of this limit idea in applications. So let's start with kind of the numerical approach. And the way we numerically do these is with a table of values. So that's what we're going to do in this example. We're going to compute the limit of the function 3x minus 5. So that's our function. We're going to do the limit as x approaches 2. And we're looking at the numerical approach. And what we mean by that is using tables. Okay. So how does this process work? What are we going to do? Well, in each of these tables, let's look at this first one. So I have some x values here, some inputs. So remember, think of x as like the input, what we're plugging in. And then f of x is what we get out. It's the output of our function. And so what we're doing is, well, let's kind of fill in this first table just to see how the process works. So we're going to take this 2.1, this x value. And we see that we want to do the limit of this function 3x minus 5 as x gets closer and closer to the number 2. So when we look here at our inputs, all of these input values, they're all x values, and as we read down the table, they're getting closer and closer to the number 2. So as we look on this right-hand side, if we kind of read down the table here, what this is showing is that x, our inputs, are approaching 2. And what we want to do is for each of these input values, we want to plug them into the function and see what output we get. So let's, as a little example, let's try 2.1. Let's plug 2.1 into our function. And our function here is this 3x plus 5. So let's take 2.1, plug it in. What are we going to get? Well, we're going to get 3 times 2.1 minus 5. Okay. Clean it up. We get 3 times 2.1 is 6.3 minus 5, and we end up with 1.3. So that would go over here. We'd put 1.3 there in the first entry in that second column. All right, well, what about the next value, 2.01? Well, let's plug that into our function and see what we get. So I'm going to take 2.01, plug it into our function. We get 3 times 2.01 minus 5, which ends up being 6.03 minus 5, which ends up being 1.03 if we do the subtraction. So we'll record that right there on our table. And so the idea of our limits is we kind of look at what happens as our inputs get closer and closer to the number 2. So we can see on this, our input column here, all of these values as we read down are getting closer and closer. These values are getting closer and closer to the number 2. And we want to figure out, well, what's going on with our outputs? What's happening with these output values? And so we try to figure out the pattern. What does it look like we're approaching? And so as we start here, we found our output was 1.3. Then we found the output, as we got a little closer, was 1.03. Well, if we get a little bit closer to 2, then our output goes to 1.003. And then if we get even closer to 2, it looks like our output goes down a little bit more. So it goes to 1.0003. And so if I had to kind of guess what was happening here, and that's ultimately what we kind of do, is it's an educated guess. But what I would say is that the output of our function looks like it's approaching the number 1. Because as I read down this column, it looks like these values are getting closer and closer to that number 1. And so in this case, I would say the limit of this function, f of x, is equal to 1 as x approaches 2. Now when we do this, all of these x values are slightly bigger. So these are all slightly bigger than 2. So the way we can indicate that is with a little plus sign on the 2. So the x values that we're using are slightly bigger. Okay. And sometimes we call this the right hand limit. And we're using values that are slightly bigger. Well, we can also use values, so we can do the same idea. We can also use values for x that are slightly smaller. And that's what we're doing over here in this other table. So same idea over here. We're looking at a table of values, and now we're using inputs that are all getting closer and closer to the number 1 or number 2 again as we read down this table. So again, as we read down this table, all of these values look like they're getting closer and closer to the number 2. And we're not going to do it, but what we could do is we could take 1.9, plug it into the function here, and we'd get 0.7. We could take 1.99, plug it into that function again, see what we get, and we get 0.97. Just kind of repeat that process over and over. And what we want to try to figure out is, well, what happens to these output values as x approaches 2? So what is the pattern here? What does it look like, these output values? What number does it look like they're approaching? And so we start off at 0.7, then we get a little bit bigger, so we go to 0.97. Then we get a little bit bigger, so we go to 0.997. And then finally, we get to 0.9997. Make sure I say enough nines there. And it looks like, if I had to guess, going in this direction, again, it looks like our function values are all getting closer to the number 1. And so when we do this, over here, we would say the limit of our function f of x as x approaches 2 is equal to 1. And the value that we are saying right here is the value that we're kind of guessing. It's an educated guess, but it's a guess in the end. And we can, since we're using values that are all slightly smaller than 2, the way we indicate that, sometimes indicate that notationally, is we put a little minus sign. So these are all slightly smaller. And if that's the case, we also sometimes call this the left-hand limit. And so something special happens when our right-hand limit and our left-hand limit are equal to the same number. And in that case, we say just the general limit here is equal to that number, in this case 1. So we need the left-hand limit to be equal to the right-hand limit. And so sometimes we're going to see it. Sometimes they're not equal, and there's a kind of a disconnect in our function. So just to kind of go back to the definition, when we do a table, we're seeing what happens to as our input x gets closer to some number, we're trying to figure out what happens to our output as our input changes like that. And what I mentioned is sometimes our limit, the left-hand, right-hand limits might be different. So if the left-hand limit and the right-hand limit are different from each other, then we say the limit does not exist. And I'll usually abbreviate this with a DNE. So that can happen. If the left-hand limit and the right-hand limit, one side of the function's doing one thing, the other side of the function's doing something else, and if they don't quite kind of match up, well, then the limit doesn't exist. And I think a picture might help. So in example 2, we're going to look at kind of the graphical approach here. We're going to look at a few different graphs, and we're going to see, well, what happens in each of these graphs? What's the limit of the function as x approaches 2? And the way to kind of graphically do this is we're going to kind of take that same approach. We're going to look at the left side of the graph, we're going to look at the right side of the graph, and see if they match up at the same point. So let's start with this first one. Here's the graph of g of x. And we're interested in the limit of g of x as x approaches 2. All right, so we're interested in what happens as x gets close to 2. And let's identify where 2 is on the x-axis. So it's right there. Now we don't actually, for limits, we don't want to know what happens right at x equals 2. We want to know what happens as we get close to x equals 2. All right, so let's start with the left side. So we can approach from this direction, and that's the left. And the idea is we're going to kind of imagine ourselves walking on the curve. So imagine just kind of standing on the curve here, and we're just going to kind of walk along the curve, and we're going to see where we go. Where is the curve taking us? And it looks like as we walk along this left-hand side, it looks like we're going to get closer and closer to this point right here. So it looks like we're going to that point. And what are the coordinates for that point? Well, 2, 1. And so because that's how it looks like we're approaching that on the left side, for our left-hand limit, I would say the limit of g of x as x approaches 2 from the left, we'll put a little minus there for our left-hand limit. We're a little bit less than 2, a little bit smaller than 2. And the function value, it looks like we're getting closer to this point right here. And so what is the value of our limit? Well, it's going to be this y coordinate. So 1. So in general, when we talk about limits, this is an important note. The limit is equal to the y coordinate of the point we're approaching. So again, if you imagine kind of standing on the curve and just kind of following, seeing where it takes you, the y coordinate, that's the value of the limit. So for our purposes, it looks like we're getting closer to a y value to this point here, which has a y coordinate of 1. So that's the value of our limit. Now we can also do the right-hand limit. So we can look on the other side of our graph, and we want to see, well, what's going on over there? So something completely different could be happening over there. And so for the right-hand limit, we're going to approach 2. We'll put a little plus sign there to indicate that we're slightly bigger. We're on the right side. And let's see what's going on over there. So we go up to our graph. We look right around x equals 2. So we pick out where we're going to be approaching. And then we kind of approach from the right side. And again, when we do this, imagine that if you were standing on this curve and you're just going to take a walk and you just want to see, well, what point am I heading towards? I'm never going to get there, but what point am I heading towards? And it looks like we're headed towards that same point. That same point, 2, 1. And so in this case, that's the point that we're heading towards, so the y-coordinate is the value of our limit. So our right-hand limit is going to be 1. And so because these two values are the same, we can say then that the overall limit, or the combined limit, as x approaches 2 is equal to 1. And again, that's because the right-hand limit is equal to the left-hand limit. All right, so let's look at another example. And I'm going to come back. When we do this, I'm going to come back. And we're going to talk a little bit more about this one, specifically what this open dot means. Let's look at the next one, though. So here's another graph. Now, same thing. We want to calculate the limit of this function now as x approaches 2. So we want to kind of break it apart. We want to look at the left side and the right side. So let's again start with, pick out the x value we're going to get close to. So again, it's going to be 2. But we're not interested what happens right at x equals 2. We want to look at a little bit to the left. Leaning my head. I don't know if it's going to show up to the... We want to look a little bit to the left. A little to the... I think it's mirrored, so it's going to look backwards. In any case, we want to look a little bit one way and a little bit the other way. So we're going to approach from the left side here. And then we're going to also look at what happens when we get close from the right side here. And again, just kind of picture yourself standing on the curve, and you're just going to kind of walk along the curve here and see where you're going. And it looks like we're going to this point right here on the left side. So what are the coordinates for that point? Well, they're 2, 1. And so from the left side, it looks like we're going right there. So our left-hand limit of g of x, as x approaches 2 from the left, and we'll put a little minus there to indicate that we're slightly smaller than 2, is, well, what's the y-coordinate for that point? 1. So the left-hand limit is 1. All right, well, what about the right-hand limit? Let's look at the right-hand limit then. And notationally, this would be the limit. X is getting closer to 2, but we're slightly bigger, so we've added a little bit extra to our inputs. And we're seeing what happens to our function g of x. Now, if we go to the right-hand side, so look on the right-hand side, look at the right-hand side of our curve. Imagine standing up there, and we're just going to walk along the curve and see where we're going. And it looks like we're going to that point right there, which has coordinates 2, 2. And so the value for our limit on that side is going to be the 2, the y-coordinate. All right, so what do we see? If we compare these two results, they're different. So these are not equal to each other. So what does that mean? Well, that means the combined limit, or the overall limit, as x approaches 2 in general, just does not exist. It doesn't equal anything. So DNE. All right, so that's kind of this second graph here, and you can kind of see what's going on. The left and the right sides, they don't match up. So, they don't come together at a nice point like this other graph did, where they kind of came together. at a common point. All right, let's try one more of these. So let's look at this graph. Now this one, there's something interesting going on. And again, we're going to do the limit of this function as x gets closer to 2. So we're going to break it down, look at the left side and the right side. And again, start by identifying the x value we're going to get close to. And we're going to look at the left side, so slightly smaller. And then we're going to approach from the right side, slightly bigger. And if we go from the left, kind of imagine yourself standing on the curve, and then we're going to walk along the curve, and we just keep going up and up and up. We keep getting higher and higher and higher. And so what's going on over here is our curve actually just keeps getting bigger and bigger. And so in this case, for our left-hand limit, we would say, well, we're doing the limit of g of x. X is approaching 2 from the left. But in this case, our curve looks like it's going up and up and up. And so we would say this limit is infinite. We're not actually headed towards one specific point. So there's not one specific point. We're just kind of heading up. There we go. So we're going off to infinity. And the same thing's happening over there on the right. So if we kind of walk along this curve, we're heading up. And so the same kind of behavior happens for our right-hand limit. The limit of g of x over there on the right, as x approaches 2 with slightly bigger values, is also going to be infinity. And what we mean by that is infinity is not a number, so g of x isn't equal to infinity or anything like that. What happens is the output of our function is getting larger and larger positive. So our output gets large positive. That's what's happening. And so because these two values are the same, well, infinity is not a number. So technically here, the limit doesn't exist. Overall, doesn't exist. But since they're both infinity, we can be a little bit more precise. So I'm not going to say does not exist. I'm going to say this overall limit actually is equal to infinity as well. So technically, each of these we could say does not exist, but it doesn't exist in a very specific way. It kind of the graph is moving up. All right. So one important thing to kind of note in each of these graphs is that at x equals 2, each of these functions is undefined. So each of these functions is undefined at x equals 2. And how do I know that? Just by looking at these graphs. Well, first of all, in this first one, there's this open dot. So if I look directly at x equals 2, if I look up and down, there's no actual filled in point on the graph. So what this open dot represents is that open dot means it's not included. If it was a filled in point, then it is included. So the fact that we've we kind of have this extra large open dot here, and it means there's kind of a little hole, there's a little missing point in our graph, and we kind of just make it extra large here just so it's noticeable, because if we didn't make it extra large, it would be very difficult, actually be impossible for us to pick out that there was one tiny little point missing on this graph. So we kind of just exaggerated a little bit just to emphasize that, yeah, right at x equals 2, there's this missing point, but everywhere else is okay. And we kind of see the same thing going on in the second graph, where at x equals 2, this point is not included on our graph, and this point is not included on our graph. We just make them extra large just to emphasize that they're there. And if we look up and down, there's no filled in point, so there is actually no point on the graph. Same kind of deal at x equals 2 over here. If we look up and down, there's actually no filled in point on the graph that we see. The curve just kind of keeps blowing up, getting closer and closer, but it never actually reaches that dotted line. And so for each of these graphs, we have kind of 3 examples where each of these functions is undefined at x equals 2. But we can still talk about what happens as we get closer to x equals 2 in each of these cases. So even though our function itself is undefined in this first one, it's undefined at x equals 2, we can still talk about what happens as we move to the left and we move to the right, or same thing over here. What happens as we get closer from the left and from the right? So it still is going to be interesting to talk about what happens to our function near x equals 2, even if our function is undefined at x equals 2. One other thing, kind of related, but just to point out in this graph. So when we have this kind of these limits at infinity, these limits where we're kind of going up and up and up, we're going to infinity, we call this dotted line that we have here, you can kind of see it, where our curve is approaching, we call that a vertical asymptote. So we'll kind of see those from time to time. So I just wanted to point that out as well. All right, so I think that's going to do it. I think we went a little long here, longer than I would have liked, but I think this is a good start for class on Monday. So we're going to continue on. So what we've done is we've kind of introduced the idea of limits. We've seen how to kind of calculate them using tables, seen how to do it graphically, and what we're going to see next is kind of how to do it algebraically, where this is going to be the kind of the most precise method that we're going to have. So we're going to start that on Monday. So we'll see you then. Bye-bye.